Here's a way to relate differentials to what we've already seen with tangent lines or linearizations. So in linearization, the game is someone gives me x and I give back an approximate y value using my tangent line formula. In differentials, the game is someone gives me not an x value, but a change in x value. So either delta x or dx, we're using them as two names for the same thing. And then what do I give back? Do I give back the new y value or even the approximate y value? No, remember, since we moved that f of c over to the other side, what we're giving back is an approximate change in y value. So we'll give back an approximate delta y value. And what is the name for approximate delta y value? That is dy. So another way to think of it, way back when we first introduced derivatives, we said dy over dx is another name for f prime of x, right? Now, we said this isn't really a fraction, but if it were a fraction, I could multiply both sides by dx, and then I could write dy as f prime of x times dx. And does that make sense with the drawing we had, or with our formula we had L of x minus f of c equals f prime of c times x minus c, and we said this was dy, this was dx, and now we have dy equals f prime times dy, anchored at some point c. Here we're saying x. In some sense it doesn't really matter, but in the example we're about to do, sometimes we'll be using c there when it's a specific number that we've chosen. So in some sense we're just taking the derivative as before, but instead of writing it as dy over dx, we're saying dy is this derivative times dx. So if we said y equals sine pi x, and someone asked, what is dy? We would say dy is, well, what's the derivative of sine pi x? Derivative of sine is cosine. Oh, let's try that again. Cosine pi x. But then there's the chain rule, because pi x is a function of x. So pi x prime dx. So that would be cosine pi x times pi dx. So that's a straightforward example of saying what is dy based on the derivative of the function and then multiplying by dx. So another way to think of this is that dy over dx is the change in y per unit change of x very locally when you've zoomed in super tight. So that's dy over dx. dy itself, without dividing by dx, you could say is the approximate change in y when x changes by dx. So let's go try that on a numeric version of this one. So we said, let's use y equals sine pi x. So go ahead and write dy, try to do it from memory even though it's on the screen. So hopefully you got cosine pi x times pi for the chain rule times dx. Let's use c equals, how about 0.1, which is unrelated to how we often use h equals 0.1. I just feel like doing something kind of near the origin here. The sine wave is increasing more quickly than a regular sine wave, and I just feel like catching it on that first upswing. So we'll use c equals 0.1 and let's use dx equals 0.05. And if you graph this, you'll see, so here's c of 0.1, and where is x? It's not 0.05, it's 0.1 plus 0.05, so it's 0.15. So dx equals 0.05. And our function is kind of curving like that, and our tangent line is doing that. I'm kind of exaggerating here. Maybe we'll do it on Desmos later to see what it really looks like. So dy equals cosine pi times 0.1 times pi times 0.05, which if you do all that arithmetic, you get 0.14939. So that's dy, the approximate change from here to all the way up here. This is such a simple situation, we can easily compute what the actual delta y is. So let's do that here. Delta y would be basically f at c plus dx minus f of c. Hopefully that looks a little familiar. Notice we're not dividing by dx because that would be per unit change in x, but we just want the total change, not per unit change. So this would be cosine of, well, let's do it in terms of f of 0.15 minus f of 0.1. If you wanted to enter that kind of by hand, you'd have to do cosine, sorry, not cosine, sine. We're using the original function here. Sine of pi times 0.15 minus sine of pi times 0.1. And after all that, you get 0.14497. So that's the actual change in y. Here's the approximate change in y. And would you say those are pretty close? Yeah, I'd be pretty happy with that in most cases. So let's switch to Desmos and see what it really looks like to scale. All right, here we are in Desmos. We typed in our main function sine pi x. We set our base location to 0.1. I couldn't find a way to type a delta character, so I'm just typing x sub delta here. And I've labeled the 2 points, and those are awfully close together, aren't they? Let's also plot the tangent line. L of x equals f of c plus f prime of c times x minus c. And we'll put that in black like we usually have been. And that one I'll do in blue. And then let's zoom in. And maybe we'll... Okay. And then what else can we say here? We said y delta, delta y was f of c plus delta x minus f of c, and that's how we got the exact change. And then we also had dy, which was cosine pi x times pi times dx. And it doesn't know what to do there because it doesn't know what this x is, but if we put in the c, then we get that value. So remember, both of those are the distance from this y value here to either this dot or that point on the line there. We'll do c plus x delta comma L of c plus x delta. So we're not concerned about the difference. We're not concerned about the difference between those. None of those are what we computed, although we want that difference to be small. Both of those are the distance between a point here. So a point here to this lower point is, think about it, is that dx or dy or delta y? Well, that's on the exact function, so that's delta y, that distance, and then dy is from this point to that upper point. And those two kind of line segment lengths are pretty close to each other.